Hi, and welcome back to another week of supervised learning. By now, we've covered a range of models that can be used for both classification and for regression problems. We've also looked at some simple approaches to testing which of a small number of predictors we should be including within these models, either by using asymptotically motivated results, information criteria, or by cross-validation. This week, we're going to explore some techniques to select which predictors belong within a model as our number of predictors p becomes large. We're going to develop and express these ideas in terms of the linear model, but the core principles here are going to carry over to many of the other models that we've introduced so far. If in our modelling situation we have p predictors available to us, then no matter what form our model takes, we have 2 to the p possible model forms to choose from. This is because for each predictor we might either include it or exclude it from our particular choice of model form. So we can see in the slide here, if we have 3 predictors, we've got 2 to the 3 or 8 possible combinations of predictors that we can include within our model. Even for moderate numbers of predictors, so moderate values of p, the size of this model space becomes very large. If we've got only 20 possible predictors that we might or might not want to include within our model, then we have a little bit over 1 million possible models to fit. This might be just about manageable if we've got a really simple model that can be quickly and cheaply fitted for every combination of predictors, but we're going to run into problems here if our model requires any reasonable amount of computational effort in order to fit with each combination of predictors. In that case, even if we have only a few predictors available to us, our computational budget or time available might not let us compare all of the possible models here, which is what we're really wanting to do, is to pick the best model from this entire model space. Again, we've already encountered some well-intentioned heuristic methods to help us navigate this issue: forward and backward selection. Forward selection begins with the null model, where we've only got an intercept and make the same prediction for every possible outcome, and then it progressively adds one predictor at a time until we reach a stage where none of the remaining predictors significantly improve our out-of-sample performance. Backward selection takes the opposite approach. We start with all predictors in the model, and then we progressively remove the predictor at each step that leads to the greatest improvement in our out-of-sample performance. And then we stop this process when there's no longer a significant improvement by dropping any of the remaining predictors. Neither forward nor backward selection is guaranteed to find us the best model overall from this collection of 2 to the p possible models, but they do tend to do quite well in practice. There are also variations on these heuristics that combine both forward and backward selection steps. We considered an example like this last week, where we grew large regression trees and then pruned them back to get rid of any additional predictors that aren't necessary to our model. So, what can go wrong as p becomes large? Let's focus on one step within the forward selection procedure. In this setup, if one or more of our predictors significantly improve model performance, then we're going to add the predictor with the most significant effect into our model. To see how this process might go wrong, let's suppose that we've got p predictors to choose from, and that each of these predictors is independent of one another and is independent of our response. None of these predictors have any predictive power whatsoever. In this setup, we really shouldn't be adding any predictors at all from the set of remaining ones that we're considering. However, if any of our model coefficients have a p-value that is less than some cutoff value, say 5%, then we're going to include the predictor that has the least p-value among all our set. If we only have one predictor that we're testing here, so p is equal to 1, then there's going to be a 5% chance of incorrectly adding that predictor into the model. However, if we've got 2 predictors and we're testing whether either of those has a significant effect, then the probability that each of these has a significant coefficient is going to be 0.05, and these are 2 independent events, so our probability of including either one of them is going to be 0.05 squared. For a general significance level alpha and a general number of predictors p, this probability of correctly stopping, so not seeing any predictors with significant coefficients, is going to be given by 1 minus alpha to the power of p. Going back to our alpha is 0.05 case, this is what we're showing in this plot. When we have one predictor, our probability of correctly stopping is 0.95. But the more predictors that we're testing here, the lower our probability of correctly stopping. We're giving ourselves more opportunities to find by chance a link between the noise in these predictors and the signal in our outcomes. By the time we get to only moderately large numbers of predictors, 10 or 20, our probability of correctly stopping has dramatically dropped, and for very large numbers of predictors, we're almost sure to include a predictor that we shouldn't. One approach to get around this problem is to acknowledge in our inference that we're performing multiple tests here. We can change our alpha value so that our overall test error rate, our probability of incorrectly stopping, is fixed to that 0.05 value that we're interested in, rather than that being the significance level of any individual test. Depending on what assumptions you make within that, you can get lots of different correction methods, and one of the most common and most conservative is known as the Bonferroni correction. So let's now consider what happens to our design matrix X as we let our number of predictors increase. And in particular, we're focusing on the case where p is still less than n here. So as we add more predictors, we're adding more and more columns to this design matrix. So it becomes wider, and the associated model becomes more flexible, because we're giving it more coefficients to estimate, and therefore more degrees of freedom. This means we're going to have lower bias on our training set, but a greater degree of model variance. Our fitted model is going to become more sensitive to slight variations in the data. When p is much less than n, our design matrix is going to be tall and thin, and as p approaches n, this matrix is going to become more and more square. When p is equal to n, then our design matrix will be square, and we'll be able to fit our training data perfectly, provided our predictors are not linearly dependent on one another. Effectively, what we're doing here is assigning each observation its own coefficient within our model. Our estimated value for yi is just going to be the observed value. This might sound great, but coming back to that bias variance trade-off, it's not really what we want to do. We want to construct a model that generalizes well, not that predicts well within our training data. And what about if we take this even further? What if we let the number of predictors be greater than our number of observations? This setup was rarely considered in the past because of how expensive data collection was, and depending on the setting that you're in, it still can be incredibly expensive to collect data. However, in some settings, this case where you have a larger number of predictors than observations is becoming increasingly common. For example, in biological datasets where you're looking at genome sequences that are thousands of values long for only tens or hundreds of individuals, or in technological settings, in online sales where there might be many more possible products to buy than there are customers to buy them. In this new and exciting setting where p is greater than n, our design matrix now has more columns than it does rows. This means that x transpose x can no longer be inverted, and we can't obtain our least squares estimates in the same way as we have before. We can see this because our linear algebra, when we're calculating beta hat here, is actually just solving n equations in p unknowns. So if our number of unknowns is greater than our number of equations, we can't uniquely specify our coefficients and find a unique solution to that collection of equations. A useful result about matrices here is that the column rank is equal to the row rank. That means that the number of linearly independent columns within a matrix is equal to the number of linearly independent rows in that matrix. In this design matrix X, we know we can have at most n in linearly independent rows, because we only have n rows, and that means only n of the p predictors can be linearly independent of one another. What this means is that we can express any one of the predictors as a linear combination of the other predictors by taking a particular weighted sum of them. This means that in other models, they might not break down mathematically in the same way that linear regression does. We can still fit the model, but we can no longer identify effects with specific predictors. That same effect might be brought about by any linear combination of the other predictors within our model. All we can hope to do in this case is identify collections of predictors that are associated with good predictions, and then further investigate whether those combinations do well on new datasets. This is like a meta version of the correlation, not causation argument. We can't say that it's this particular predictor that is driving this particular correlation. So we've introduced a lot of problems that arise as the number of predictors becomes larger. In the rest of this week, we're going to focus on ways that we can overcome some of these problems. In particular, we're going to focus on two different classes of technique. The first is called regularization or penalization. These are two equivalent terms for adding a penalty to constrain our search space and enforce there to be a unique solution to this collection of simultaneous equations. We'll consider several different forms that this penalty might take and the properties of the resulting models that they give. In particular, we'll look at the ridge, the lasso, and the elastic net penalties. We'll also consider the case of projecting our set of p covariates down onto a lower dimensional space. We'll be taking linear combinations of our covariates to produce a smaller set of covariates that still captures most of the information within the entire collection. Here we'll look at two options, using principal components of the design matrix and using a partial least squares approach. Thank you very much for your time, and I look forward to seeing you in the next videos.